Hello everyone, welcome to lecture 5. From this lecture, we're actually moving to the second half of the course with the focus on online learning and some of the applications in others. And then the very first application we're going to see is a very classic one. I call it dynamic pricing with demand learning. So far we talked about sequential posted pricing, which is basically the case that you're a seller, you want to sell the sequence, you want to post a sequence of prices to maximize your revenue, but then we assume that the seller has full knowledge about the value distribution or demand distribution. But from this picture, we imagine that the seller is in a stationary environment, meaning that the stochastic behavior of the buyer won't change over time. But then the seller doesn't have information about the underlying distribution of the value. And now the goal of the seller is to experiment with prices and learn as it tries to also maximize the expected generated value. So it is about basically exploration, aka learning and exploitation. So you're posting prices, you have to experiment different prices in order to learn the demand. At the same time, during the experimentation, as a seller, you would like to gather enough revenue, and the question is how. So we are going to start with a very simple case, very simple case, and it's actually pretty unrealistic. But I think you're going to learn a very cute technique in this part. And that is the setting when I'm a seller, there is no supply constraint, there is a sequence of buyers that are arriving. Imagine buyers are myopic, so meaning that they post a price. If the value of the buyer is above the price, it's going to accept, otherwise going to reject. And I even assume that the buyers' valuations are all the same. It's like the same number V, and you have this sequence all around from time 1 to time n. And the goal, you don't know that unknown value, and you're trying to experiment with prices in order to maximize the generated value. This is a classic Leighton-Kleinberg paper. And a trivial solution that comes to mind is binary search. I'm going to mention how to do that. But then I'm going to show you can actually beat binary search by exponential factors. You can do exponential better than binary search and use the structure of the pricing problem. Then there is also the i.i.d. version of the same model when there is no supply constraints. Buyers are arriving. This time, buyer values are drawn from the same distribution, but are independent draws from that distribution. I'm not going to teach that, but I think it's very instructive to take a look at the paper after we cover the first bullet and see how they managed to get similar type of results for i.i.d. case. Instead, we are going to talk about the more realistic setting, which is i.i.d. values and limited supply. So I'm a seller. I have k copies of the same item to sell. There are i.i.d. buyers arriving over time, and my goal is to maximize the expected revenue. So we have studied this setting, if you remember, under the assumption that as a seller, you know the underlying distribution, and we learned that actually an anonymous pricing, fixing the price at some certain quantile, will give you almost the entire revenue. Competitive ratio of 1 minus 1 over a square root 2 pi k could be achieved using just a simple price at the quantile equal to q over n of the distribution, k over n of the distribution. But this time we don't know the distribution, and the question is how to do that. In the first half of this course, basically part 1 of the course actually, we learned UCB algorithm for multi-on bandits. And here we are going to use the UCB idea to design this dynamic pricing algorithm. I call it UCB pricing. But it's actually kind of a clever way of UCB in this context. It uses the structure of the problem. It's not just thinking of it as a multi-on bandit and running this. And in order to analyze that, there are different steps. So part of the analysis is actually quite similar to the way that you usually analyze UCB in multi-on bandit. And then there is a second part of the analysis, which is coming up with some sort of like concentrations. For UCB in the multi-on bandit, you basically only need Chernoff bound. And that's the concentration inequality that you need in order to finish the proof. Here it turns out that actually you need to be more careful. You need very strong concentration bound for Martingales. And if you naively use the Azuma concentration inequality, which is more or less like Chernoff bound, it's the additive version of Chernoff bound, then you won't get the type of result that I'm going to show. And instead, you need to look at the multiplicative concentration inequality for Martingales, aka Bernstein inequality. So in the last half an hour of the lecture, we're going to talk about these concentration bounds and how to use them in order to finish the proof of the regret bound of this algorithm. Is anyone familiar with this kind of concentration bound for Martingale, especially the Bernstein inequality? Have you seen those? Okay. To this day, I never actually used Bernstein in any research I have done. I've always been using Azuma. But when I was actually preparing for this lecture, I think it was for the first time that I realized this inequality is way more powerful than this. And you will see that in this lecture. I don't know, have you ever used Bernstein? But that's Chernoff, right?
Yeah.
I mean, Warren's point is that, it was the exam question, right? The last exam question. So the last exam question that you guys had, you were using multiplicative version of Chernoff bound. There is also this additive version of Chernoff bound that is slightly weaker, which is also more for the special case of i.i.d. random variables. Bernstein is kind of as powerful as a multiplicative Chernoff bound, but it's works for Martingale, not only independent.
Have we decided square root?
What's that?
Square root.
Oh, who is going to scribe today? All right, perfect. Thanks. All right, so let's start by the first problem. So, what is the problem setup? Imagine we have n buyers, fixed value v, and this is unknown to the seller. So there is no supply limit or no supply constraint, meaning that in principle, the seller can sell to every single buyer. But then the seller is going to maximize the revenue, so somehow is creating virtual supply scarcity in order to maximize revenue. So no supply constraint. Buyers 1, 2 to n arrive sequentially. Seller posts the price PT for buyer T. If V is greater or equal than PT, then let me write it down this way. So if V basically greater or equal than PT, then sale happens, and reward of the seller will be equal to PT, and there will be a feedback, which is the feedback is equal to 1, meaning that the sale happens. This is the only thing that the seller has, not the value. Yes.
How many items do you have?
1.
Only one.
No, n in principle. So no supply constraint means that at every time I can actually sell.
So if somehow the value is high, it's better to always say, even with
If the value is high,
with a low price than just exploring the high prices without selling. Because we are losing something. Yeah.
if the value is high, we set the price low, then the sale is going to happen, but you're not making.
Why not making money?
Because you get the price.
Yeah, it's low, but it's better than that. So it's good to start from low prices. Yeah.
Versus high price. Well, also it depends on, well, so you're making money, but then probably you still have a regret compared to the best value. So I agree with you, that's posting lower prices better than posting higher prices in some sense. There is asymmetry in that sense, because from lower prices you can still make money, from higher prices you cannot. But there's still, even from low prices, you can accumulate returns, because there is a difference between the value and the actual price you're posting.
So everyone has the same value.
Yeah, fixed value, just on. And if V is smaller than PT, then no sale. So reward is going to be 0, and the feedback is 0, meaning that there will be no sale. Okay, very basic stuff. So what would be a natural algorithm here?
Should the seller know something about B?
I
interval.
only know it could. So assume value is bounded. Actually, in this lecture from now until the beginning, always assume that values are bounded with 0 and 1. These are between 0 and 1. You're absolutely right. But I can change this upper limit to h, and or just the same thing was true, but rather than that, yes.
It's binary search, as you said.
Right. So binary search is the most natural thing to do. Binary search pricing. Meaning that I maintain an interval, let's say A and B or L and H of the candidates, the interval that the candidate value should be in that set. So L is 0 at the beginning, H is 1, then I always query the midpoint. And based on that, I update my search interval until, let's say, the length of the search interval is 1 over n, little n. So after that, it doesn't matter which point you're going to output, the difference between the value is going to be 1 over little n. So from that point until the end, the total regret you accumulate is just going to be a constant. It's all about how many rounds it takes for you to get to the point that the length of the search interval is ordered 1 over n. Let me write down what I just said. So we're going to maintain this interval L and H, initialize that to be 0, 1. At each time t, post the price pt, which is equal to L plus H divided by 2. If sale happens, that means the value was greater than the price, then let's L to be et and doesn't change H. If no sale, that means the value was smaller than the price there, therefore doesn't change H and doesn't change L and change H to B. Is it clear? What does the algorithm do? Now claim. Maybe before that I should define regret. So regret is simply, what is the maximum you can get here? If you know the value? What price should you post if you know the value?
Just the V.
V, right? And then the maximum you can get is V times N. So what I define as regret is the reward of the algorithm, the right number. So we say, let me actually get a definition. A bit more definition. We say a pricing algorithm has regret bound f of n if expectation, it can be randomized algorithm. If the expectation of summation t from 1 to n, p of t, x of t is greater or equal than v times n minus f of n. So what is x of t? X of t is basically the indicator that v was greater or equal than pt or not. And the expectation is over the internal randomness of the algorithm. For example, you can randomize in your sequence of prices. This is a deterministic algorithm, but in general, you can have random. Now, claim binary search pricing has order log n regret. let epsilon to be 1 over n. After k equal to, let's say, log n buyers, the search interval h minus l has a length which is equal to what?
2 to the negative k.
So 2 to the minus k. Which is that's epsilon. Right? So summation t from k plus 1 to n pt xt so think about it in this way. So there is this interval that v lands in, the length of the interval is epsilon. Let's say all the time I actually go with the lower limit, I post that price. That's what you basically are gonna do. So if you post this price, then it's gonna get accepted, but then you might accumulate some regret, which is bounded by epsilon. But then epsilon is 1 over n, then this is gonna be this minus, let's say n minus k plus 1 times v is gonna be bounded by n times epsilon, which is 1. But then you're gonna incur regret bound in the first k rounds. And I can say summation t from 1 to k pt xt minus, let's say, k times v is at most k, right? Which is log n. Therefore, total regret is order log n. Very simple. Is the proof clear? Basically, after your search interval is small enough, then you're really not incurring that much. If you go with the lower limit first. But now, what can we do better? Which part of the binary search can we improve? And the intuition is kind of actually similar to what you mentioned, meaning that somehow there is an asymmetry between low prices and high prices. Low prices still generate revenue, so in that sense, I prefer them over high prices. And here's the algorithm. So let's call that double binary search pricing. So the double binary search pricing starts with essentially the search interval L and H, and let's say initialize that with 0 and 1. It also has a precision parameter. Called epsilon. And at the beginning, you initialize this to be, let's say, half. Okay. So here is what it does. Basically, you will have a couple of phases. This is going to be phase 1. going to be phase 2 until the end. So in this phase, your precision parameter is going to be epsilon. In the phase after that, your precision parameter becomes epsilon squared. So you basically zoom in a little bit more. And I'll tell you what do this phase is. For now, and then phase 3 is basically epsilon to the power 4. And in general, when you look at the phase k of the algorithm, you will have epsilon to the power 2 to the k as the precision parameter. So what is this precision parameter? So this precision parameter is precision in a linear search to find basically a candidate interval for your price. So in phase 1, what does it do? Or in any of these phases, let's say, for example, I pick phase k. At this point in the algorithm, there is a search interval. Let's call that again L and H. So this is L, this is H. So divide the search interval. This thing. Epsilon to the power 2 to the k. Maybe k. Right. So let's call this epsilon k. And we have L of k and H of k to kind of show that this is for phase k. So in this phase, you just divide this interval linearly into subintervals of length epsilon k. So I'm going to have a bunch of intervals. So this is epsilon k, this is epsilon k, so on and so forth. And what does the algorithm do? So the algorithm starts posting a price, which is first this one. Then it's going to post this price, it's going to post the next price, so on and so forth. If these prices are all going to get accepted for some reason, until you hit one price that gets rejected for the first time. Then, so imagine that all of these prices get accepted for some reason. Then, if this price gets accepted for the first time, the next one gets rejected. So then the algorithm knows that, hey, my value should be between these two prices because this is the first price that got rejected. This is the last price that got accepted. So therefore, my value is going to be in this interval. And by identifying these two, you can go to the next phase. So this point is going to be your LK plus 1, and this is going to be your HK plus 1. Okay. So, and then when you go to the next round, you just look at the square of the previous epsilon. So epsilon k plus 1 in this round, in this phase is going to be epsilon k to the power 2, and you continue. And the algorithm maintains an interesting invariant. So algorithm always guarantees that HK minus LK, basically the length of the search interval, is at most so epsilon. It's just a constant. So epsilon k actually. Right.
Not if that point.
So in phase one, I will have, just give me a second. So in phase one, I have epsilon, epsilon 2. And what I'm going to have is that then this is epsilon, this should be 1 over epsilon number of prices.
This term is correct. Then this is the actual dimension.
We have epsilon squared here.
Those are the actual squares, yeah,
So what I want is basically in phase one, I'm going to have epsilon, phase two, epsilon squared, phase k
Ek minus 1.
e to the power 2k minus 1. Yes, I can. And then what I want is this to be at most epsilon to the power 2k actually. Let's see. So if this is epsilon to the power 2k, how many of these subintervals I'm going to have? 1 over epsilon to the power k minus 1. Right.
This is not, is this 0 to the
To the k. That's what we think. If you guarantee this variance, that's the coordinate, the side of the hk minus lk that was epsilon to the power 2 to the k, then the number of subintervals
But at the
in phase k.
the first phase, this is not even true. H1 minus L1 is just 1 minus 0, 1, right?
So at the beginning, this is equal to, I think everything will be true after phase one. So in phase one, you have basically
I think it should
epsilon
be-
equal to half. So you have two, so you have 1 over epsilon number of phases, each one, 1 over epsilon number of intervals, each one with size half. So you have 2 intervals of size half. Then you go to the next phase. I think it's good. The
It's,
number
it should be 2 to the power k minus 1, right? So at H1 minus L1 is half. Is that it?
Yeah, but he's saying is that like H1 minus L1 is 1, right? Because
Is it
it's
1
the
or
star,
half?
we don't have any.
right.
So there you would need 2 to the k minus 1. So you would get 2 to the 0, I think, right?
Let me tell you what I'm trying to get.
It's an offset of 1, so like.
It's an offset of 1. I mean,
Is it an
I
offset?
don't think it even matters.
So what I'm trying to say is that, well, so in the phase one, I'm going to have epsilon equal to, so in each phase, I have L and H, and then there is also an epsilon. So then I look at L plus epsilon, L plus 2 epsilon, all the way to H.
Right.
And then the difference between the two is epsilon, and you kind of want to have the length of this thing to be a square root of epsilon, so that the number of them is equal to 1 over square root of epsilon.
I'm just saying the invariant you wrote, it should be 2 to the power k minus 1. Right? Because at time 1, you have the hk minus h1 minus l1 is
But
epsilon.
then I think this is just k.
Okay,
And
then this should start from epsilon square. I think it was correct, 2 to the power k minus 1, but there you just change it to 2 to the power k minus 1.
so this is going to be epsilon minus 1. Is it putting k minus 1? I think the k is correct, but I think this is not correct. So epsilon k squared is equal to epsilon to the power 2 to the k.
So hk and lk is for phase k or phase k plus 1?
Minus 2?
Honestly, does it matter? Like, because it's 1 now.
I mean, you can just That epsilon k is larger than what you have.
Right. Yeah. So this is going to be epsilon to the power k. This is going to be to the power k minus 1. And I guess what I wanted here to say, this is going to be,
This is what we get.
this is going to be half in phase 1. Here, this is going to be epsilon, this is going to be epsilon 2, so on and so forth. I think this is now.
But epsilon is how?
So epsilon at the beginning is equal to half.
Should be epsilon squared the next.
So this is epsilon squared.
So then what we get at the end, right, of the phase. Versus we have after the end of phase 1, that's.
Call phase 0 and everything is fine.
Yeah, if you add a phase 0.
At phase 0.
You call phase 1 phase 0 and everything is done.
Okay.
Yeah, phase 0 has length 1, phase 1 has length of.
But I guess all I need is that the epsilon that is used in this phase should be
Square, yeah.
a square of the length of the interval, which is let's not even call this whatever. Just like epsilon to the power that's phase k. All right, phase k is epsilon to the power 2 to the k, is epsilon to the k minus. Okay, but again, all I need is that if the distance here between the two prices is, let's say, epsilon to the power 2 to the k, I want the length of this interval to be epsilon to the power 2 to the k minus 1, so that the number of subintervals in phase k to be bounded by 1 over epsilon to the power 2 to the k minus. Okay, so let's see what's happening here. So let's see what the algorithm. So the algorithm starts from this epsilon. Then at the beginning, this is the search interval. So it increases the prices by epsilon until it hits the first point that the price doesn't get accepted. That would be the H for the next phase. And the price just before that is going to be L for the next phase. Then it looks at epsilon, square that epsilon, goes to the next phase, and continue the same iteration. Does it make sense what the algorithm does?
So in the first period, there are 2 prices.
Exactly. So in the first period, there are 2 prices.
And then 4.
Right. So it starts with 0, then this price, and then there are 4, and then identify whether we should look into this interval or that interval. And then in each of them now, epsilon becomes 1/4. So you will have how many prices?
Still 2.
Still 2, right? So this is half divided by 1/4. So it's going to be 2. But the number of so basically the number of prices is going to be equal to 1 over epsilon of the previous one, right? So number of prices is going to be 1 over epsilon to the power 2k minus 1, which is the epsilon of the previous one. Yes.
Can you explain this drawing? How can epsilon to the epsilon squared? I don't know how to write this. To the power k can be less than that one. Epsilon
Epsilon is
is
less than 0.
That's it. This is 0 and 1.
Yeah.
yes.
So this is basically if you call this number alpha, this number is the square root of alpha. The square root of alpha is larger than alpha. Like 1/4 the square root is half.
Epsilon is between 0.
Actually, this is 0 and 1. I start with half, I square that, it becomes 1/4, 1 over 16, so on and so forth.
If the top is 1 over 4, the bottoms are 1 over 16.
Right, so I guess this is probably a better picture. If the distance between prices is epsilon, then the length of this interval, the entire interval is going to be 1 over epsilon, and the number of prices I'm going to post is going to be 1 over the square root of epsilon. All right. So now let's see what happens. What would be two sources of regret in general in this dynamic pricing problem? So one source is when a price gets rejected. So if a price gets rejected, of course you are going to lose regrets. How many times the price gets rejected in this algorithm? So let's two sources for regrets. Source number one, number of prices that get rejected. How many prices get rejected? At most? Okay. All right. So I didn't tell you when to terminate, right? So you start narrowing down this interval until you get to the point that, again, the length of the interval, let's say, is smaller than 1 over n. So when it is smaller than 1 over n, I always go with the lower price. And from that point until the end, similar to the analysis of the binary search, you won't accumulate a regret more than n times 1 over n. So that means that this algorithm stops the search once epsilon to the power 2 to the power k, which is the length of this interval, or let's say 2 to the power k minus 1, becomes smaller than 1 over n. But the moment that it becomes 1 over n, it's going to stop. That means, what case? If epsilon is half at the beginning, then let's take 1 log. So 2 to the k minus 1 will be equal to log of essentially n, and k will be order log n. So what I'm trying to say is that if you are squaring the epsilon each round and you start from epsilon equal to half, then after order log n number of phases, you're going to get to a point that your search interval has length at most 1 over n. Right. So now that you stop at these points and k is equal to order log n, so how many actual phases you have? At most log n, right? And in each phase, only one price gets rejected. That's the definition of a phase. So you start increasing the price from the lower limits until you hit the first time that the price gets rejected, then you go to next phase. So therefore, in each phase, one price gets rejected. The number of prices that get rejected, this is, so this is at most number of search phases. And the search phase ends when the length of the search interval is at most 1 over n, which takes order log n phases. So this is going to be at most order log. But this is only one source of regrets. What is the other source of regrets? So there are a lot of times that you have a price that they get accepted. But then for each such a price, you are going to incur a regret. What would be the regret be?
Selling below the value. So like the difference between like the true value of whatever you're selling for.
Perfect. And let's say a price in phase K gets accepted. What would be the maximum distance between that price and the value?
Epsilon
K. B minus LK.
Right, so the length of this interval, the length of the basic hk minus lk in that phase, and that is at most epsilon to the power 2k minus 1. How many of those prices you have at all?
HK minus LK where HK minus the part.
1 over epsilon to the power 2k minus 1. So each one contributes epsilon to the power 2k minus 1. You have 1 over epsilon to the power k minus 1 of them. So in total, all of them at most will give you 1 unit of regret. So each phase the contribution of all the prices that get accepted to the regret is at most bounded by 1, is bounded by 1. Therefore, the total regrets, let me write down. Guys, suppose price PT gets accepted in phase K prime. Then the regret from PT is upper bounded by H K prime minus L K prime. And we know this is at most epsilon to the power 2 to the K prime minus 1. Number of prices PT in phase K prime, because of this is at most 1 over epsilon to the power 2 to the power K prime minus 1. As a result, the total regret from accepted prices in phase K prime is going to be at most the number of those prices multiplied by the regret for each one. It's going to be 1 over epsilon to the power 2 to the power K prime minus 1 times epsilon to the power 2 to the power K prime minus 1. So they cancel, is at most 1. And then how many phases do we have? Log log n. Therefore, total regret from accepted prices is at most order log log. And that gives us the following theorem. Double binary search algorithm. Has order log log n.
Can you please repeat the first part of the binary search?
The actual binary search?
Yeah. Shouldn't we accept after that time?
Even after the search interval is small? Yes, I guess it really doesn't matter what you do, but to just kind of really safe side, this is a variant of binary search you should think about. So when the search interval is small, just go with the lower price.
No, it matters actually, because if you're gonna suppose until that time you go up near 1, and then the value is right before 1, so you always reject.
So at each time post that, this is going to be a while loop, right? So let me write one line here. After h minus L is smaller than 1 over n, post PT equal to n.
But even this would work, I think. What you had earlier. You
Yeah.
have to do that.
Okay, so basically what we did.
I mean, even though it gets rejected, it doesn't matter.
Yeah, but the value is high. Your regret is high.
Right?
Suppose this sequence, the value is 1 minus 1 over
Oh, wait.
2 to the
No,
power.
it's half plus epsilon. I think half plus epsilon.
So then it's constant or half plus 1 over it?
Half plus, it's very close to half. So the first time it's cell, but We never cancel again.
What's very close is n. Like 1 over n is basically what we plus close. You're saying it's smaller than 1 over n?
Oh, no,
So the search interval becomes 1 over n.
Oh,
But
I
if you
see.
go with the
It's slightly
upper
above
limit, then
1
you are gonna
It's like
lose
1
all
minus
that
2,
revenue.
I see.
So you have to get the revenue all the time. But then the regret that you lose from an accepted price is going to be bounded by 1 over n. You have at most n of those, so that's going to be bounded by n. So posting PT equal to L is right.
Okay, so what I see is that basically what we did is have the loss from being rejected and we have the loss from selling cheap, and we balance the two, be the same in every round.
Yeah.
Which gives us this really.
This is actually very much aligned with Mohammad's intuition. Let's try to have an algorithm that has way more number of accepted prices than number of rejected prices. You basically get one rejected price in each phase, and then you get a lot of accepted prices. But then you control it in a way that the regret from those accepted prices is bounded by 1 over their number in each phase. This is a very elegant algorithm, I should say. Okay, so, but you know, this setting I would say is very unrealistic in the sense that who says the value is going to be fixed over time? And then there is this theorem from Kleinberg and Leighton, 2007. If VI's are i.i.d from a distribution F, and distribution F is regular. We already know the definition of the regular distribution, meaning that if you look at the revenue curve for the distribution in the quantile space, in the probability space, it should be constant. If that is the case, then there exists a randomized pricing strategy. Let's call that A, such that the expectation of the revenue of A is greater or equal than n times P star times 1 minus f of P star. I'm going to define what the P star is, minus order square root n log n. So what is P star? So P star is basically the one price that maximizes the single round revenue, the monopoly price. So arc max of P times 1 minus P for all the P's that are between 0.
Do we know the F or not?
You don't know the F.
Don't know.
No, that's the point, right? So if you know the F, you always know
That's
this
just
price.
that. Okay.
It's again for the dynamic pricing without knowing the thing. So now, I mean, I'm not going to show you how to prove this theorem and what is the algorithm, but instead we are going to switch to limited supply setting and try to design an algorithm for that. You raise this whiteboard, tell me what the setup is, and then some simple observations before we introduce the algorithm. All right. So the setup, we have n buyers. Values are denoted by, let's say, V1, V2, all the way to the end. Vi is our i.i.d, drawn from the same distribution F. We also assume that, let me write it down, assumption. Support of the distribution F is equal to 0 and 1. I'm going to make another assumption. This assumption. F is regular. And for those of you that remember, we basically define the revenue curve in the price space to be P times 1 minus F of B, which is equivalent to P times the probability of the event that the value realized on the distribution is greater than the price. Now, if I call this quantity Q, then you can say, all right, so with a little bit of abuse of notation, R of Q would be equal to Q times F inverse of 1 minus Q. This is basically the P. This is really abuse of notation because here the input argument is P, here the input argument is Q, but that's all right. And then we say distribution is regular if the revenue curve is concave in the context. So this is 0, this is 1. Let's say this is a particular quantity Q star, and the line here has a slope which is equal to R of Q star divided by Q star, which is a quantity I'm going to call it P star output price. Okay, so this is the assumption of the underlying distribution. Back to the setup, there is one seller with K less than or equal than N units of the same item. And then seller adaptively both prices P1 to Pn. The goal of the seller, maximize revenue of these prices. And as a random variable, what is the revenue that you get? So the revenue of P1 to Pn is basically the following quantities, can be summation T from 1 to some N. You will have P of T multiplied by X of T. So what is N? What is X of T? So X of T is the indicator that the value at time T is greater or equal than the price. And what is N? N is the first time that you either hit the last buyer or you run out of supply. So N is defined to be the max. It's going to be defined to be it's a random variable, stopping time. It's a maximum, let's say, N prime between 1 and N, such that summation T from 1 to N prime of X T is at most K. So the goal is to maximize the revenue, but obviously we try to compete with the benchmark. And What's the benchmark for revenue here? An offline benchmark? Any suggestions? So if I know the entire pool of the buyers, what would be a meaningful optimal benchmark?
Max K.
What's the most powerful benchmark here? We already saw it in lecture 3.
I mean the VCG on virtual value.
Optimal Myers notch, right? So let's say the benchmark is the optimal Myers notch, meaning that I have n buyers, each one has a value drawn from the regular distribution. I have k items to sell, meaning that at the end of the day, no more than a subset of, a subset of the buyers that has size less than or equal than k can be winner. And the goal is to maximize the expected value you can get from these buyers through any Bayesian incentive compatible auction. Right? So the benchmark is going to be optimal Myers auction. Let me define another benchmark. Benchmark prime. It's what I call the best fixed price in hindsight. So what is that benchmark? So basically, I'm looking at, let's say, a price. Fine. Let me also introduce a notation. I'm going to use it a lot of time. So 1 minus f of p, I'm going to denote this by the demand at the price p or d of p, just for simplicity. So what is my other benchmarks? I actually look at, let's say, posting the same price p all the time and look at the expected revenue you can get from that price. So what that number would be, so, let me not write it down because then I have to introduce a lot of it. But the revenue from P is basically the expected revenue of posting price P in all the time steps or for all the buyers one to one. Let's call this optimal. All right. So what do we know about the relationship between the revenue of, let's say, the best fixed price in hindsight and optimal Myers? Does anyone remember? There was one particular price that was performing very well when you were selling K units of the same item.
It was the expectation of the maximum of the virtual values. Wait, no.
Let me remind you what that was. So we were looking at, let's say, Q bar equal to K over N. And then we had this price P bar, which was essentially the inverse demand at probability quantity K over N. And in one of the previous lectures, if you remember, we showed that the revenue you can get from P bar was greater or equal than 1 over K expectation of the minimum of K and some random variable X times out, where this X was a Poisson random variable with parameter 1 over K. Do you remember this one? And then we showed this is going to be, we use the Sterling approximation. So this was basically equal to, I remember the function for something like 1 minus k power k divided by, let me not write that down because I don't remember the exact function. But it was almost 1 minus 1 over the square root 2 pi k times opt. So basically what I'm trying to say is that if I look at the Vickers benchmark, which is the revenue of, let's say, the best price in hindsight, which is going to be an upper bound on the revenue of this particular price, this is almost equal to opt if k is large. This is a multiplicative approximation, but you can say, well, so this is greater or equal than opt minus order square root k, right? Because opt is at most k, the revenue of selling k items to buyers whose values between 0 and 1 is at most k. Therefore, this term is, this is opt minus opt divided by square root 2 pi k, opt is at most k, therefore that gives you order square root k additive error. But the multiplicative one is strong. All right. So this is not that bad. Maybe we can work with this benchmark. Let me introduce another benchmark. Benchmark double prime. But this is not the real benchmark. This is actually an estimation for benchmark prime. So not a real benchmark. But an estimation for benchmark, right? Let's write it down. So I'm going to use V of P. Sorry for notation. I'm trying to use the same notation as in the paper I'm covering. And by the way, the paper, we write it down. So it is Ovaio Doggy Feinberg Smithkins 2015. It's called dynamic pricing with limited supply. Yeah, so in that paper they use this notation BP, so I'm going to stick to that, but it's really not a good notation. So BP is defined to be the following quantity is equal to P times the minimum of K and N times E of P. Let's see if you understand this quantity. In some sense, this is trying to estimate this expectation. But it's really not exactly an expectation. So the way it thinks about it is, hey, if I do not impose any inventory constraints and I let my pricing strategy with fixed price P to sell all the time, then my revenue is going to be P times N times DP. Because DP is the probability that you sell the item at each time, times DP, that will be revenue times P, and then you have N time instances to track. But then you have to cap this quantity because at the end of the day, you have K items to sell. This is why it looks at the minimum of K and the expected number of times that the algorithm will close up by constraint. Yes.
Your benchmarks are all online algorithms when they know the distribution.
Correct. This one is actually offline algorithm, so you can't run offline marathon in an online fashion because you need to elicit all the values in order to make the final decision who are going to be the buyers that has the maximum virtual value. So this is offline. But you're absolutely right that if I know the underlying distribution, then these two are this is an online benchmark, and this is just the fictional benchmark, but you can definitely run it in your head now.
On the first one.
Yeah.
Shouldn't it be the expected of maximum of the top K?
Top K virtual values, but you cannot run that in an
No,
other function.
top K
Virtual
values.
values,
By this.
because we are maximizing the revenue. Do you remember the characterization, the reduction from revenue maximization to welfare maximization by replacing values with virtual values?
Upper bound benchmark. Jen was drawing Jetsons. So double prime is upper bound on prime, right?
Double prime is an upper bound on prime by using NSA device. Yes, that's true.
Yeah, I'm also considering if you know the distribution, why you don't solve the DP to get the benchmark.
Good question. You can do that, and apparently it's not necessary. Basically, I mean, you're absolutely right that if you know the distribution, you can also solve a dynamic program that gives you the optimal sequence of prices, maximum revenue. That's also a good benchmark. It's somewhere between the optimal Meyer zone and, let's say, benchmark prime. I'm going to show you that the gap between the two is actually small. Therefore, the benchmark to have in mind is also going to be in the E. In fact, we know the gap between the two is small because of this term, right? So you can't, and this is not going to be the bottleneck when you think about the regrets at the end. There are going to be other sources coming when you try to compete with this benchmark without knowing the demand. Therefore, there is really no difference between improving the benchmark here. You can improve the lower order terms in your regret bound, but not the main order term. All right. Okay, cool. So let me do one thing. I already showed that benchmark and benchmark prime are in a multiplicative sense and additive sense close to each other. Let me actually show that this quantity is also a good measure of this revenue by using a simple concentration bound. Okay, so lemma. This is what we always call Chernoff bound, or Chernoff bound, Chernoff bounds. Suppose x1 all the way to xn are independent random variables, and the support is between 0 and 1. Let expectation of summation t from 1 to n xt to be equal to mu. Then we have the following inequality. For every delta, I believe between 0 and 1, but I might be wrong, maybe it's between 0 and half. I think it's 0 and 1. So the probability that the absolute value of summation t from 1 to n xt minus mu is less than or equal than delta times mu is at least 1 minus 2 times e to the power minus delta squared divided by 3 times mu. This is a concentration bound that we're going to use. I'm not going to prove that, but trust me that Chernoff bound is correct. So now, Now suppose, consider posting the price P without enforcing the supply constraint. Then define xt to be the indicator that Vt is greater or equal than P. Then we have Qt to be the demand at this price. And I can say the probability that summation of xt is t from 1 to n minus n times dp is, let's say, greater or equal than some delta times dp. Delta times n times dp. And let's call this value, right? So this is my view. Is at first 2 times e to the power minus delta squared divided by 3 times mu. Now, if I set delta to be for some reason, I'm going to make this to be, let's say, 1 over k. That means if I set delta to be square root of, let's say, 3 log k divided by mu, then that happens. 2k. 2 over k, right? Okay, that's fine. So basically, you can say with high probability, I can say, let's call, I can say, yes, summation t from 1 to n of x of t minus mu is greater or equal than order square root mu times log. And with high probability really means with probability 1 minus 2 over k. Therefore, if I look at the number of sales that happen when you enforce the capacity constraints, the number of sales when you enforce supply constraints, this is equal to the minimum of k and summation t from 1 to n xt, then this is going to be greater or equal than the minimum of k and right. So right. So I guess what I want to show that is the other way. So the retarded is greater or equal than minus of this thing. So therefore, with high probability, this is greater or equal than minimum of k and mu minus square root mu log k multiplied by some constant. which I don't, I just like replace it with 1 for simplicity. Right, and then this is not difficult to show. This is actually greater or equal than the minimum of k and mu minus a square root k dot k. This is just a case analysis. Imagine that k is smaller than this quantity, k is between this quantity and mu, and k is greater than mu. And if you do all the cases, this is equal to false. So I leave this case analysis because it's just like simple algebra. I replace mu here with k. All right, so what I'm trying to say is that really these two benchmarks are, the benchmark delta and benchmark prime are close to each other for any price T. So claim for every price P, for every price P, we'll have revenue of P to be less than V of P, and it should be as follows. The revenue of P plus order a square root k log k. Is it clear why that lower bound on the number of sales implies this? So first of all, this one is trivial. Basically, either you can use the answer inequality, or you can just simply say, well, so V of P, P times K is definitely an upper bound on revenue of P because this guy never sells more than K. At the same time, if I don't imply any supply constraint, the revenue is just going to go up. And that will be P times N times VP. So both of these policies, in terms of expected revenue, are going to be upper bounded by revenue of P. Therefore, the minimum of thing is going to be also upper bound. It's going to be an upper bound on the revenue of P. And then the difference between the rev of P and V of P is really the difference between this quantity and this quantity multiplied by P. And then P is bounded by 1, so therefore the gap is going to be bounded by order k dot k, or the square root k dot k. Does it make sense? Is everyone following the calculation?
Can you please repeat the upper bound?
Where the upper bound is coming from?
Yeah.
Yeah, so basically this is P times the minimum of K and mu that I have there. This is P times X, where X is the number of sales. And we know X and minimum of K and mu in an additive sense, your distance is bounded by a square root K log K, and P is bounded by 1. Therefore, order is square root K log K. Okay. So this is nice because I can kind of now measure how good the price is if I know the demand. And if I don't know the demand at each time, by just estimating the demand function from the past, we can kind of have a handle of how good each price is in terms of revenue. So from now on, we are going to actually we are going to work only with this function somehow. So let's do the following. Let's have a break maybe for 8 minutes. Then we will be back and see how we can design an algorithm analysis using constraint.
What's the time by our watch?
The brand,
No, what's the time?
the time, 3:30.
Because if you add 8, you don't get any round number.
That's right.
Oh,
I make it 8 so that when people are late, you don't.
oh, I see.
I know.
Didn't reach out to you?
What? I know, sorry, I wasn't available yesterday, so let's see. Do you want to chat with me after the class? Let's do that. So now we want to design a pricing algorithm where kind of the measure of effectiveness of the price is a function v of p. Now, we need to do something I call the pre-processing step, which is essentially discretizing the space of price. So processing step. For discretization. Set of prices. So in principle, you can have any prices in 0 and 1. So right now that I'm going to define this set curly p, which are all the prices of the form, let's say some delta times 1 plus delta to the power I, such that p is between 0 and 1. I guess the way to think about that is, I start from, so this is 0, this is 1. I start from the lowest price, delta. The next price is going to be delta times 1 plus delta. Then the other one is going to be delta times 1 plus delta squared, all the way to, let's say, hit somewhere here, delta times 1 plus delta to the power some k. And I call that set P, so these are going to be set of aka active prices. So first of all, what do we know about the cardinality of this set? Imagine delta is a small number. So k can be as large as the quantity where delta times 1 plus delta to the power k is equal to 1. It's something like log of 1 over delta in base 1 plus delta. And this is ln of 1 over delta divided by ln of 1 plus delta. And ln of 1 plus delta, if delta is a small, is more or less delta, so this is roughly 1 over delta times ln of 1 over delta. And now I'm going to make an assumption. Later we are going to use that. So the assumption, we don't want to have a lot of prices. So let delta to be at least 1 over n. Oh, yeah. So I'm going to decide on this delta, but whatever it is going to be at least 1 over n, so that 1 over delta is at most n. And if that is true, then this is going to be bounded by 1 over delta times ln of n. I still keep this 1 over delta because I haven't told you what's 1 over delta is going to be, but whatever it is going to be at most n. It might be a smaller, but it's going to be at most. All right. So keep that in mind. Let's try to design an algorithm. So consider some pricing assumptions. constraint T, I can look at 2 quantities. So first one, I call N T of P, and the other one is called KT of P. So how are they defined? So NT of P is the number of times. Constraint pricing strategy is called that algorithm. So NT of P is the number of times that algorithm A has experimented price P during 1 to T minus, right? So at some time T, I look at a particular pricing strategy, NT of P is the number of times that the algorithm has picked this particular price. And all the time, imagine that I'm just looking at prices in this active set. Later, I'm going to show you why this is almost without loss of general. Restrict your attention to those prices. Okay, so is this clear? Just like I count how many times my algorithm has outputs particular price. And then KT of P is basically at most NT of P is the number of times that the algorithm has experimented price P during this interval, and price P was accepted at that time. In some sense, like number of times that the algorithm has sold the item, but at price. All right. So if somebody is asking you, hey, what would be your estimate of the demand at price P, P of P, given these two numbers? What would you say? K over N, right? So now we define D hat at time T for price P. We basically KT of P divided by NT of P. If you have identified, let's say, a price where the probability of sale is equal to K over N, because if you knew the distribution, you could always post that price, right? The price that the probability of sale is equal to K over N, and we already know that it is a pretty much good price. So it is very close to optimal price. At the beginning of the lecture, I thought this out, but we don't know what that price is. So if this number is around K over N, you're kind of in a good shape. If it is very further from K over N, so your price is going to be further from the price corresponding to quantity K over N, and you have to be careful about it. But the good thing about this quantity is, in order to calculate this for all the prices, you don't need to know the math. You can just look at the history of the sales and estimate the demand of that. Okay. So now, what are some candidate algorithms that come to mind, given this quantity? What is the most naive way to use the demand function? So we already discussed the V function that they raised is kind of a good metric to tell you how good a price is. The reward you can get from that price and expectation is represented by the V function, but the V function requires D. So the most natural thing to do is plug D hat into the V function and then go with the price that maximizes that estimation. Right? So greedy solution is P of T would be the one price in the set curly P that maximizes essentially V of P, which is P times the minimum of K, and let me actually use the V of so the minimum of K, P times the minimum of K, and N times V hat T P. Right. So this is one way to consider the process. So now if you think about, for example, this as a multi-bounded algorithm, This is analog of the greedy algorithm in the multi-arm bracket context, meaning that I have different arms. I look at the historical performance of all the arms and I put the one that has the best historical performance. But this is usually not a good idea because of exactly the same reason. Here it's not a good idea because it doesn't give you enough exploration. Sometimes you want to pull the arm that you haven't pulled that much to just give a chance to that arm to give you samples. And this is how you induce exploration to your algorithms. So one strategy for doing those, as we learned in the part 1 of the course, is basically going with, again, an index-based algorithm, but this time, rather than using only the average performance as the index, you look at the upper confidence bound of the parameter as your index. So now that gives us the UCB pricing. So UCB pricing is basically the same thing, but rather than using the actual estimate of the demand, I use the UCB or upper confidence bound of the demand. So PT would be argmax of P in the kernels P, and I maximize the V function when I plug the upper confidence bound as the demand function. Minimum of K and N times the UCB T for price P. And how does the UCB value is defined? So by the way, I call this quantity the index UCB T for price P. How is the upper confidence bound defined? So usually we think of this upper confidence bound to be the actual estimate, the average, we have TP plus some confidence bound. For now, let's call that RT of P, and this needs to be defined. And we'll define this. And this is one part that the algorithm is different from this, the classical simple multi-arm, the way that we define the confidence. All right, so given how RTP is defined, then the rest of the algorithm is well. What is one natural way of defining RTP if you want to just naively follow UCB recipe? Has everyone seen UCB before? Do we have anyone that hasn't seen UCB at all? It's fine if you haven't, right? Have you guys seen, you guys been in the course before? Okay. Yeah, so the idea, Paulina, is basically, as I said, rather than going with the average estimate, you go with an upper bound to kind of be a little bit optimistic about each arm. And this optimism will give a chance to that arm to be pulled, even though it wasn't the best historical arm. And that induces a little bit of exploration so that you learn about all this. And why this is a good idea, actually, you will see the proof here. So the part of the proof of the pricing, UCB pricing, follows the proof of the actual UCB algorithm, but then the rest is not.
Can you please explain again that equation? What is gamma T?
I haven't yet defined it. So the idea is you add a term here that such that with high probability the actual DTPs. So this is similar to the confidence bound that we had before, right? So you add a confidence bound such that the demand for each price P with high probability is in the confidence interval. So the length of this guy should be somehow inverse proportional to the number of times that this price has been experimented before. To capture the fact that if a price has been experimented before, you know more about that price, therefore the confidence interval is smaller. And you shrink the confidence interval with a rate that comes from concentration.
Can you please also explain why you multiply P to that minimum?
Oh, because well, so think of like the reward you can get from putting this price. This is the VP function if D hat was replaced with D. So VP was a surrogate for the expected revenue you can get by posting that price at outbound. If I remove P, this is just about how many times the price is accepted, or how many times the item is sold at this price. But you really need to look at the reward from the price, and that is when the expected revenue is. All right, so if you naively follow the recipe of UCB, it suggests the following RTP. So it suggests RTP to be something like, let's say, order square root something like, say, 6 log n divided by NTP plus 1. All right. The problem with this RTP is that sometimes you are looking at prices where their demand is actually pretty low. And for those prices, this confidence bound can't actually be valid in the sense that, yeah, so I don't want to show you why this doesn't work. But roughly speaking, the intuition is there will be something going wrong when you think about prices where the demand is actually small.
So basically the confidence interval itself is big with respect to D hat, and then you need to choose more and more for that bad price. And then that.
Yeah, so they need a confidence bound that when the demand is small, the confidence bound also shrinks. When the demand for the price is small, the confidence also shrinks at an appropriate rate. But then that also doesn't work because I could just, for example, add D hat TP here, and then it would have that property. But then it would be so good to be true that this is actually a confidence bound, because you need a very powerful multiplicative concentration bound when the demand is small. Therefore, neither of these two solutions work. And the one that works is the one that I'm going to write. So the correct version of confidence bound. And by the way, so I encourage you to think about different ways of defining this confidence bound to see where the elegancy of this paper is coming from. I actually tried last night to come up with an alternative version that is a little bit simpler. I tried a few candidates, all of them failed badly. And I'm not yet convinced there is no other way of coming up with a confidence bound here, but somehow this is very smart. So they look at the confidence bound, which is a function. So RTP is equal to, sure, right. It has a base which is equal to alpha divided by NTP plus 1, and I'm going to tell you what the alpha is, plus something similar to this. The square root of alpha D hat TP divided by NT of P plus 1. And for now, think of this alpha as something that is going to be order theta log n. And we're going to decide on this alpha later.
So Bernstein kind of.
Yeah, exactly. I think they had the idea of using Bernstein inequality, and that's how you kind of came up with this. Exactly. All right, so the final algorithm is the following. Let me write it down. So UCB pricing. At each time t, pick the price p from the curly p such that pt is maximizing the index, the UCB index. And UCB index is defined to be the estimation for the demand plus RTP, and RTP is defined as that. All right, so this is the algorithm. So here's the theorem that we want to prove in the remaining 15 minutes. Define with regret, just be clear what do we mean by regret. So definition, regret of pricing a strategy A is basically f of k and n are bounded by if we can say the expected revenue of the pricing strategy A, and you know how to calculate expected revenue, so I'm not gonna open this term, to be at least optimal milestones revenue minus f of k and n. So I'm looking at the regression expectation, and then theorem, UCB pricing as regret guarantee of f of kn equal to order k to the power 2/3 log n to the power 2/3 if distribution f is regular. I want to add a comment. If the distribution f is not regular and you still compare the performance of the UCB pricing with the best fixed pricing hindsight, the same result is true. The only thing that you cannot say is that the best fixed pricing hindsight is close to optimal margin. So that is the step that you essentially need regularity of the distribution. But if your benchmark is benchmark prime, the best benchmark prime I had on the whiteboard, then you really don't need regularity. You can just compete with the best fixed pricing.
So if k equals n, this does not
Yeah.
go back to the.
Right. So good. So if k is equal to n, that would be the previous problem. And even Kleinberg's results was a square root n log n.
Yeah.
So in that sense, this is weaker. But this works for everything. But for a small k, actually there is a regime of k for which this is actually information theoretically tight. So they have a lower bound in the paper that shows, if you want to get a regret bound for all k's, then there is a regime. I forgot what the regime of k was, but in that regime, this is actually tight. For large K, you can do better than that. You can bring down this exponent all the way to half and this exponent to half, square root n log n. If K is small, you can still do better. They show in the same paper that for K is small, I think you get something like a square root. Yeah, something K times the square root log. Okay. So if K is small, you can get K square root log n. If K is large, you can get a square root n log n essentially. But there is a regime in the middle of it.
Did you prove all of them are right?
They did, yeah, they did. But I think one thing that comes out of this conversation is, what would be really like the right function for the information theoretic lower bound on optimal pricing. It hasn't been answered in this paper. I need to double check some of the follow-up work to make sure that it hasn't been answered in the literature, but I don't know the answer off the top. Yes.
For saying it is tight, they actually provide some distribution that is kind of worst case.
No, for any algorithm, not for this. So they basically say there is an instance in which the pricing algorithm can get a regret bound more than this. And it can get less than this.
For any algorithm, there is a distribution that is no better than.
Right. Actually, I think one of their bounds is a universally good distribution or universally bad distribution. But then for a small inventory regime, a small supply regime, they say you give me an algorithm that works, and I can find an instance such that the regret bound will be exactly equal to K square root log. And then the other result, the square root n log n is also times for unlimited supplies. So let's try to prove this. So the proof, in some sense, starts by the same type of attack strategy that you usually have when we think about UCBS style bandit algorithm, which is saying, okay, so there are certain good events that if they have happened, then I can deterministically finish the rest of the analysis. So let's try to find those good events. Once I find those good events and I assume that they are true, then I found the regret, then I go back and show that my good events are happening with high probability using concentration. Okay. So let me start by writing down those good events. So the first one is that so I want my confidence intervals to be valid, meaning that for every t and for every p, when I look at the absolute value of the difference between p hat t of p and the actual demand at the price p, I want this to be bounded by the confidence bound, RT of p. But here's one other thing that they're going to ask for. In the confidence bound, we have d hat. So they need another thing to be true, which is, if I look at the version of RTP that I replace d hat with dp, it should give you an upper bound on the confidence. So it should be at most 3 times alpha divided by ntp plus 1 plus the square root of alpha times p of p divided by ntp plus 1. In some sense, what they want is not only the confidence bound to be valid, but also it will be within a constant approximation of the version of the confidence bound that you had plotted the true demand in this function. For this one, you actually can show this using simple Chernoff bound, and we're going to do that. So simple Chernoff bound. Is enough. Then they need two more things. So the first one is about the number of sales. So you basically make that the number of sales that you have minus the demand. So what we want to have is that if I look at the summation, t from 1 to n, x t of algorithm minus summation t from 1 to n, demand at the price that is posted by the algorithm. This should be bounded by the square root b log n plus the square root log n. That's log n. And what is this b? So let me make some definitions here. So xt is going to be the Bernoulli variable that indicates that time t the sale is going to happen if you relax the supply constant. So xt is simply the indicator that vt is greater or equal than pt. And then demand at pt, it's demand at pt, so it's the probability that vt is greater or equal than pt. And to be exact, this is basically the expectation of xt conditioned on all the previous prices. Because once you condition on all the previous prices, or even I can condition on the previous state, right? So if I condition on the previous state, x1 to xt minus 1, then the price at time t is determined. So this is going to be the d of pt. And d is a random variable, so it is the summation t from 1 to n of d of t.
In the first thing, we are just writing RT less than equals to 3 RT.
No, so here I have replaced e hats. And then the second thing they're asking for is that if you look at the summation t from 1 to n x tpt, so this time I'm not only looking at number of sales, I'm looking at the actual revenue if I relax the supply constraint and I compare that with t from 1 to n pt, d of pt, it should be bounded by essentially the same thing, t log n plus log. And you can probably see why, for proving at least 2 and 3, we need to think about Martingale, because d, pt, and xt are both of them random variables. So in fact, condition on the previous realization of x1 to xt minus 1, then pt is now deterministic, and that gives you the probability that x is equal to 1. In other words, if I look at, let's say, xt minus d of pt, I call this vt, then I can say the expectation of vt condition on x1 to xt minus 1 is indeed 0. So think of this as difference of a Martingale sequence where the filtration is generated by x1 to xt. If I define, for example, s of t to be the summation t prime from 1 to t of z of t prime, then s of t is a Martingale sequence with respect to sequence x1 to x. And the first inequality is really a concentration inequality for that Martingale. Yes.
Why did you discretize P because solving that argument become easy?
No, because here I'm saying for every P, and this should happen with high probability. So at some point, I'm going to take a union bound over all the possible prices. So if you have a continuum of prices, then you can't do union bound. But once you discretize and you let the curly P to not have that many prices, then the loss you get from union bound would be managed. Is it clear why that sequence is a Martingale and why to prove 2 and 3, I need to really think about 2 Martingale sequences? I assume everyone knows what the Martingale is. If you don't know, this is actually the definition. So we say a sequence ST is a Martingale sequence with respect to filtration X. If you look at the different sequences, ZT in this case, then the expectation of ZT at every time T condition X1 to Xt minus 1 to be equal to 0. If this is greater or equal than 0, that defines a super Martingale,
No, sub
Martingale. I'll always make that easier. And then the other one is a super Martingale.
It's the obvious opposite of what
Exactly. I mean, it's greater, so it should be super, right? But it's actually sub. Right. It's kind of like capturing here, you have 0 in expectation condition history drift, and then you add these numbers together. How does that vary? And you want to actually look at the probability that, so that thing with 0 conditional drift at each time is further from 0. So if it's not that far from 0, then this should be true. This one is about a slightly different Martingale sequence. So here, for number 3, you basically look at, let me write it down, Z tilde of T to be equal to PT times XT minus D of PT. This is another funny Martingale sequence because when you look at the expectation of Z tilde of T condition on X1 again to XT minus 1. Well, condition on the history of sake, price is deterministic, so it comes out, and then you look at this expectation. This is already 0, so that gives you again an error. So you can, what I'm saying here, you can multiply this Martingale sequence by anything. You can multiply the different sequence of your Martingale by any function of T, as long as that function is only a function of the past phase. And still you will have a multiple. And yeah, and then the name of the game is really trying to look at the concentration. And this is the part that we are going to use Bernstein inequality. For these two, we're going to use Bernstein inequality. I hope I will have time to get there. Otherwise, I'm going to refer you to the paper. I'm glad that I mentioned it about here at least. Any questions about this part? So from now on in the analysis, I assume 1, 2, and 3 are correct. And given that, you want to show the rigor. More definition because I haven't defined enough number of things in this lecture. So let's define V star to be basically not the argmax, the max of V of P for all the P's in the curly P. And then we define P star to be the argmax of V of P for all the P's in the category P. So therefore, V of P star is basically this. All right. Then for every price P, I'm defining the gap for that price, the delta P, similar to the way that we usually get the gap between the two arms in UCB, to be V star divided by N minus P times D of P plus So now let's try to understand how much how much we lose in each time t at a price p. So lemma, so I want to show that nt of, let's say, pt multiplied by delta of pt, when pt is the sequence generated by my algorithm, is at most order log n times 1 plus k over n times 1 over delta of pt. And this is basically the crucial lemma in the analysis. One crucial lemma in the analysis. Proof. Yeah, so for any p, we look at Vp. So Vp is the p times the minimum of k and n times Vp. Yes.
Actually, is that for any t?
For basically for any t for any pt. So I'm looking at basically some time t and the price of an exponent at that time t.
Shouldn't we need only for the last time and enough pt times the delta?
It's actually true for any time, I think. But I only need it for last time.
Yeah, we need it for the last.
Right, but that, it really doesn't matter. But you're right. I mean, I can. What I care about is really at the end. And if that helps, let me define this notation. So n of pt is equal to n of pt, number of times that price pt is experimented in total. And let's try to actually show this one. But I think it doesn't matter. All right. So here's the so when the confidence bound is valid, then you can say, well, so this is going to be at most p times the minimum of k, n times dp plus rtp. Sorry, d hat tp plus rtp. And then this is what we call the IUCD of P. And again, this is at most times the minimum of K and times D of P plus another RTP, 2 RTP. Because of the fact that there is a symmetric bounded difference between dp and d hats. Now let me write this down. I actually don't want to erase this part. Anyway, hopefully it's going to be that difficult to write it again. Now here is a crucial observation. So we know that if PT is the price that we are posting, then we are maximizing the UCB index. So IT UCB at price PT is definitely going to be greater or equal than, let's say, the V at the one particular price I'm interested in, which is the P star. Right? And if it's not clear what I'm doing, so I'm basically first saying that the index of UCB TPT is greater or equal than the index of UCB T and any other price, let's say P star. And because of the first inequality here, we know for any price P, the UCB index is an upper bound on its VP, so this is greater or equal than V of P star, which is equal to P star. And then you also know that from the second inequality, IT UCB of PT is less than or equal than PT, the minimum of K, and then N times E of PT plus 2 RT PT. Right? That's the last inequality there. Now, if I combine 1 and 2, then I can say, hey, so PT times the minimum of, and I divide this thing by N, K over N, and then I have D of PT plus 2 RTPT. This is going to be greater or equal than 1 over N times this. And this is the key inequality. This one I'm not going to erase, hopefully. So 3 consequences from this inequality. Number 1, the price you're posting, this algorithm, if the good event happens, is always greater or equal than V star divided by K. So you never actually post really a small price if V star is large. Why is that? Because, well, so this left-hand side is at most K over N times PT. So if PT times K over N is greater or equal than V star divided by N, the N cancels, so PT is going to be greater or equal than V star divided by N. That's one consequence. The other one is that, hey, if I look at essentially dt of PT or delta of PT, let's say, yeah. So if I look at the delta of PT, remember, so the delta of PT is basically the difference between 1 over N times V star and PT times D of PT. So this delta is going to be at most 2 times RT of PT as we kind of expected. This is another property that we always see in UCB analysis. But the gap between the one that UCB proves and the optimal R is bounded by 2 times the length of the confidence interval. Is it clear where is this coming from? Again, so you use this part. So these times PT is greater or equal than 1 over n times V star. And rearranging the term, you get that delta PT is at 1 to 10 power. Then the third one is kind of a little bit interesting. So it says that if you have an arm that is not strictly worse than, so say if you have an arm that is strictly actually better than, sorry, if you have an arm that is strictly worse than, right, if you have an arm that is strictly, if you're putting an arm that is strictly worse than optimum, then the demand cannot be larger than K over N. It should be actually strictly smaller than K over N. Let's see, and in fact, actually, this is about any price. Yeah, this is about any price. So if you have any price that the delta P is greater than 0, then the demand is going to be at most K over N. Where is this coming from? So what I'm saying is P times PP for any price P should be at most 1 over n times V star by the definition of V star. And we already know that
Well, you just have this price, right? Because you're still selling K and you're getting a higher price.
but I think the price should be pulled before actually.
This is a deterministic statement. This is a deterministic statement. Right?
This is a deterministic statement, yeah. Where is this coming from? Oh, so it comes from the fact that, right, so we know PT is greater or equal than, let's say, right, so we know PT is greater or equal than V star divided by K. If delta PT is strictly greater than 0, then that means V star is strictly greater than n times PT V of PT. Right. Divided by K. And that's it, right? So now you cancel these two, and that implies that V of PT should be strictly less than K over N. So basically, it says that if the algorithm is experimented in price that is strictly worse than the optimal one, then the probability cannot be actually more than K. So it's going to be among the quantiles corresponding to 0 to K. K over N. Okay. So the rest of the analysis is a little bit so now we basically show our level, right? So if price P as n of P greater than 0, basically imagine I'm at some T. I'll just say is one price that has been experimented at least once by the algorithm. Then define tau to be the last time price posted by the algorithm at that time is equal to. So obviously, n of that p is basically equal to the n tau of p tau plus 1. Okay. So now I look at the delta of p tau. So by property number 2, I'm looking at time tau, right? Yes.
What, can you please repeat why that strict inequality is correct?
Why is it true? Yes,
I agree the first one.
right. And then the assumption was, you have a you're experimenting a price PT that is strictly based on the optimal price in some. Delta PT is strictly greater than 0. So that means n times PT times d of PT should be strictly smaller than d star.
Anytime.
Right? N times PT times dpt should be strictly smaller than d star. And that gives you that. By simply using number 2, this is going to be at most 2 times, or at the time tau, the last time that you experimented the price, p tau, and this is equal to, or actually at most, there will be a number 3 here, there will be a number 2 from there. So number 3 is the upper bound in the Goody band. So I'm going to use the actual upper bound, alpha divided by nt p tau plus 1 plus the square root of alpha times the demand at point pt divided by p tau divided by n tau p tau plus 1. So in the confidence interval, I actually didn't use the half, I used the upper bound that we had in the Goody band. And this is why the factor 3 is here, so we'll have a factor of 6 here, which is fine. Now think about this then, right? So we want to think about essentially n tau of p tau times delta p tau. And either this is 0 or this is 0. So if this is 0, we are good to go. So we are only considering prices that have been experimented bonds, so we are already assume n of pt is not 0. Now if delta pt is 0, again, this is clearly true. If delta pt, delta p tau essentially is greater than 0, then we know d of p tau should be at most k over n. This is from fact 3. And as a result, we can say delta p tau is at most 6 times alpha divided by n plus a square root of alpha divided by n times k over n. I just call this guy n. So the rest is just case analysis. Let me consider 2 cases. So case 1, suppose alpha over n is greater or equal than the square root of alpha over n times k divided by root of n. In that case, we can say delta p tau is at most 12 times alpha over n. And therefore, n times delta p tau, which will be at most 12 times alpha. So keep that in mind. So this is case 1. Case 2, if it happens that alpha divided by n is at most the square root of alpha over n times k over little n, then delta p tau will be at most 12 times the square root of alpha k divided by and small n. Therefore, delta p tau squared is at most order square root order alpha k divided by n times n. Therefore, n times delta p tau is at most alpha times order alpha times k divided by n, and then there will be also a factor 1 over delta p tau. So this is the second case. And then I don't know which case is happening. What I can say is, no matter what, n of delta p tau is at most the max of the two. And the max of the two is upper bounded by a summation. And alpha was theta log n, if you remember. In the confidence bound, I said alpha is, think of it as really log n. So combining everything, we just concluded that n at the time, the last time that we experiment the price times p of the price times the delta of p tau is at most order log n, which is the alpha times 1 coming from here, and then you will have a k over n times 1 over delta p tau. And this is the proof of the lemma. Does it make sense? So I'm considering two cases. In each case, there is an upper bound. Therefore, there is a universal upper bound, which is the max of the two. The max is upper bounded by the sum. Absorb these constants in your definition of alpha. Alpha is going to be this order log n. And then the rest is going to be 1 coming from here, and the k over n times 1 over delta comes from. That's it. Yes.
I'm going to make that delta squared and then
This was a square root here, so now it's delta squared is that.
how you get last one, sir?
So move one of the deltas here, keep 1 on the left hand side. So you have 1 over delta. Yeah, I think for people that are very much familiar with UCB proof, this is the case 2 was pretty similar to UCB analysis when you want to show that the regressive boundaries. All right, so why am I interested in this term? Because the summation of these things over all the prices that we experimented will be kind of a good measure of the regress bound. And let's see that last step. But before I need another lemma, so lemma. Suppose rev is the revenue of our pricing strategy, is the revenue of UCB pricing. If all good events happen, then we want to show that rev is at least summation t from 1 to n p of t d of p of t minus some function g here, g of k Right. So what is g of k? So g of k is square root k log n plus log n. The proof is not that hard, but let me actually do it. So a few cases. So case one, suppose we have sold every item, summation t from 1 to n, xt is greater or equal than k, right? So if you ran out of supply at some point, then this is a good thing, because then you can say, well, my revenue, the actual realization of the revenue in that sample path was equal to P of, basically it's greater or equal than any lower bound you can have on prices times the number of items that you have sold, which is K times, what is the lower bound on the prices? I know all the prices are greater or equal than V star divided by K, so it's going to be K times V star divided by K. So this is the scenario that actually your revenue is greater than V star, and therefore it's greater or equal than any term here. But then suppose you don't sell everything, so therefore you can say my revenue, case two is when the summation xt, t from 1 to n is strictly smaller than k. In that case, you can say my revenue is now equal to the summation t from 1 to all the way to n, p of t, x of t. And because of the good, one of the good events, this is going to be greater or equal than summation good event number 3. T from 1 to n, p of t, d of p of t minus the g function at the point d, where d was summation t from 1 to n, d of t, if you remember. Now, case 2a, if d is, let's say, smaller than k, then we can say rev is greater or equal than summation t from 1 to n pt d of pt minus g of k, and we are good to go. Right, because increasing this to k only increases this gap. And then if d is larger than k, then you can use the other concentration bound. So this is going to be case 2.b. If d is larger than k, we already know that, well, so x minus d was, right, so we know x, the number of times that you sell because of the good event number 2 is going to be equal, is going to be greater or equal than d minus g of d. That was good event number 2, if you remember. And d is greater than k. D minus g of t is actually monotone in k, so this is going to be greater or equal than k minus g of k. So this is the number of items that we sell. Therefore, revenue is going to be greater or equal than the minimum on p, which is v star divided by k times x, which is v star minus gk divided by k. And this is just like greater or equal than v star minus gk. This is in a better bound. And in this case, you're also good to go because v star is always greater or equal than summation t from 1 to n PT, D of PT. So what was the point of this lemma? The point of this lemma is that when you think about revenue, of the actual revenue under good events, you can switch to this surrogate objective and you're not going to lose that much. Because G of K is kind of a square K log n, so it's fine to have that kind of regret bound. And then when I work with this kind of surrogate as my revenue, then delta P comes into the picture, similar to UCB analysis. And because of the previous level that I proved, I can bound my regrets. And this part of the analysis is very dry. Sorry about that. The version I'm presenting is a little bit better than the paper. But still, I share the sentiment with you before at this point. Let me quickly finish the proof. Right. How to bound the regret. All right, so we start from revenue. So revenue is going to equal than previous lemma. Summation T from 1 to n, P of T, D of P of T minus G of K. This is going to equal than essentially T from 1 to n, PT dpt minus V star divided by n plus V star minus GK. So this is equal to V star, think of this as the optimum solution, minus a bunch of things. So the first one is summation T from 1 to n, V star divided by n minus PT dpt. If I make this greater or equal, then I can say this is at most summation T from 1 to n, the delta that I get at that experiment minus plus G of K. And then rather than just looking at all the prices you're experimenting, you can look at the price space and say, hey, this is equal to V star minus summation over all prices in my active set. And now I have to look at N of P times delta of P. And N of P, think of it as the number of times that your algorithm is actually experimenting the price. For any price that has been experimented at this point. So this plus sign is because I'm looking at all the prices that they have been experimented only once. Plus G of K. So all prices have been posted once. Right, so now we want to bound this regret bound. So define P of epsilon to be all the prices in the curly P such that delta of P is greater or equal than epsilon, for some parameter epsilon that's going to be set. So I'm kind of like looking at two sets of prices, those that are low demand, those that are high demand. And then I can say my regret bound is upper bounded by G of K plus sum over all P's that are in P epsilon n of delta times n of p times delta of p plus all the p's that are not in p epsilon n of p times delta of p. Right. This is going to be upper bounded by epsilon times n, because delta p is at most epsilon and the number of such prices at most n. What about this one? So we're going to use the upper bound that is. So basically, this is upper bounded by summation p in p epsilon, and then I have this order log n term multiplied by 1 plus k over n times 1 over delta. So this is going to be basically cardinality of the set p epsilon times order log n for the first term. And then for the second term, it's going to be k over n. And we know because in all these prices, the gap is actually large, then 1 over delta is not larger than 1 over epsilon. So this gives us the g of k plus epsilon n plus, what do we know about the number of prices? The number of prices is bounded, if you remember, by log n divided by delta. So it was ln of n divided by the parameter delta we used in the discretization. And then we'll have, yeah, so, right, so this times ln of n plus k over n times 1 over epsilon. Let me write them separate. So it's going to be log n squared divided by delta plus k over n log n times 1 over epsilon. So this is regret with respect to essentially the best price in the curly set. But what about the best price per se? So if I just look at the optimal price, how far the optimal price would be from the optimal price in the set P star? So basically what I'm trying to say is the following. I have prices 0 to 1, this was delta times 1 plus delta, all the way to delta times 1 plus delta to the power I. So I have a small regret with respect to the best of such prices. And now you look at the actual optimal price, let's say P star, the optimal P star T. So it is between two of these guys. Delta times 1 plus delta to the power I minus 1 and delta times 1 plus delta to the power I. Or it might actually land here, so it might be the case that this guy is even smaller than delta. So I claim if it is between two of these prices, then the revenue you get from P star is going to be at most, the revenue you could get from the lower price if you multiply that by 1 plus delta. Because basically you look at two prices that are not far from each other by a factor of 1 plus delta. So if anything was accepted by P star T, it's going to be accepted by the lower price, but only at a slightly lower revenue by a factor of 1 plus delta. So therefore, the revenue from P star delta, and this revenue cannot be far from each other by a factor of 1 plus delta, but more than a factor of 1 plus delta. And the revenue of this price is smaller than the revenue of optimal price in the curly set P. So putting everything together, there is a gap of multiplicative gap of 1 plus delta between the revenue of the actual optimal price and the optimal price in the set curly P. Only if the optimal price is larger than delta. If it is smaller than delta, then I claim actually the optimal price is kind of useless, because how much you can make at most delta in each round, and you can sell at most k items. So therefore, the revenue of the optimal price is at most delta times V star, or delta times k, right? So again, so if this is the case, then the multiplicative gap between V star and the revenue of the optimal price is 1 plus delta, and the additive gap is going to be delta times V star, and V star is at most k, so it's going to be at most delta times k. If you're in this scenario, then P star is already at most delta, so opt is at most delta times k. I hope I could convince you basically to switch from the best price in the curly P to the actual best price. The additive gap in regret will be delta times k. So that means if I look at the regret with respect to actual optimal price, then this is going to be upper bounded by the same thing, this function, plus an additive delta times k. And this is why you need to be careful about epsilon and delta. So what you want to do at the end is basically matching this epsilon n with delta k. So you set epsilon to be delta times k over n, one choice that you have to make. And then how to pick delta, then you basically pick delta so that L squared divided by delta will be equal to gk. If you set delta to be something like k to the power minus 1/3 log n to the power 2/3, then you get the final result, which is this order k to the 2/3 log n to the 2/3. Yeah, sorry, I went a little bit over time. So this is basically the proof, modulo the fact that I didn't show you how to prove the concentration inequalities. If you refer to that paper, it is actually on the Canvas site. So the rest of the proof. Check a section in the paper in Babayo, Dogme, Kleinberg, 2013. I forgot the section number, but they have the experience section on how to use concentration in Bernstein inequality to show the property 2 and 3, and how to use Chernoff to show the property 1. And that finishes the proof. Yes.
One thing I didn't get, so where does the new definition of UCD play a difference?
When you want to show 2 and 3.
Okay, so concentration.
In the concentration interval. Yes. You need a confidence bound such that if your estimate of the demand is low, the confidence interval becomes smaller. So ideally, you would like to have a confidence interval of the form the square root of, let's say, log n d of p divided by n of p. So this is the ideal confidence interval you want to have. But this is good. This is but this is too good to be true, because if the demand is small, you can't actually show that basically dp hat plus minus this thing is a confidence interval. I mean, a dp is going to be here with probability, with high probability. And then they had this other term that will be added to compensate for that, and then they use the Chernoff to show.
The other term is just a smaller order.
Not all the time. It is a smaller order if D hat P is small. If D hat P is large, it can actually be little.
If P star is a
The other way, if the hat P is small, the other term actually becomes
Yeah.
substantial. If the hat P is large, then you have to consider.
if P star is such that you sell K units. So then the PT is always above P star. So somehow you're charging higher prices because you said PT is bigger than D star over K. So then somehow you're always charging higher prices.
Exactly. Because here started kind of like this optimal price times n times k over n. I think so, right? So think of here star as some price here star times n times the demand that you expect.
It's min of K comma that. So if you actually sell all of the
So you're always above the optimal price.
that's what okay, yeah, that's what
Exactly. So you're always above the optimal price, and then you start learning that.
interesting with high probability I always sort of play above the operator. It's interesting.
I promise the next lecture is going to be cleaner. Yeah, actually, next lecture is going to be on a topic that the proof is probably like very short. And I try to just like give you more context.
We never promise ahead of time.
Yeah,
Think the
but
expectations, right?
That's worse, yeah, surprisingly.
this one, I think there's just a lot of concentration required. I didn't even get to the concentration required.
It was president, so. I think it was-